Hello everyone, I'm Gülşen and my group mates are Hamza, Emin and Ahmet Furkan. Today we will talk about aluminum alloy 775. Firstly, we will mention chemical composition and area of applications. Secondly, examine the analysis of the stress-strain curve, then mechanical properties, and finally, we will talk to fracture type, explain and prove whether it's ductile or brittle. Aluminium 7X series alloy, also called aluminium zinc alloy, due to maximum zinc quantity ranging between 5.1 and 6.1%. Table 1 shows the chemical composition of the aluminium 775. As you have seen in the table, in mass percentage, it has about 0.4% silicon, 0.5% iron, 0.2% titanium, 1.6% copper, 0.3% manganese, 2.5% magnesium, 0.2% chrome, 0.65 others, and balanced aluminum. In the past 70 years, aluminum 775 series alloy materials used for components of marine, aerospace, and automobile applications are missile tail cone, turbine casing, automobile engine casing, bicycle components, fuselage, glider airframes, rifles for the American military, shafts for lacrosse sticks, inline skating frames, etc. High-strength alloys are one of the main utilizers in the automobile and aerospace industry because of their enhanced performance and significant weight savings. Aluminum alloy 775 T6, which is high strength and lightweight, is one of the most cost-effective and widely used in aircraft wings and fuselage, and also in automobile industries.
So if we take a look at the stress strain analysis of aluminum 775 and its alloys, we can first start to define different kinds of analysis that we're going to take place, that are going to take place or that we're going to test. The first ones are going to be quasi-static and dynamic compression, and the other two are going to be quasi-static and dynamic tension. So if we look at the test, that's taken here, we can see that the material that was investigated was aluminum 7075, and in order to improve its workability, its cold workability, it's at a O annealed temper state. The material tested was followed by a slow cooling into the furnace to room temperature. And as you can see here from the table, the testing conditions for the quasi-static and the dynamic state are given, as well as the height and the inner diameter, as well as the outer diameter. And as you can see by the picture here, it's a picture of the tested specimen. And if we go further and we can see the graphs of the quasi-static and dynamic compression, we can see on the left-hand side the quasi-static compression process at several strain rates are indicated by different colors, and we can see that they're fairly similar, and there's not that much change in the strain rates that are seen in the graph. This, in contrast with the dynamic compression graph as seen to the right, has very, very different or very, very significant changes in the lines. As you can tell, the red, the blue, and the green lines show how much the strain rate affects, and the dynamic test affects the stress strain graphs of these tests. And if we go over to the quasi-static tension test, this test was done with different specimens other than the ones mentioned before. This test specimen was in the subsize ASTM-E8 configuration, and that were fabricated with 12.7 millimeter diameter aluminum rods, and it was at room temperature with a strain rate of 1/F. And as you can see from both of these graphs, the left-hand side uses aluminum 7075 T651, and on the right it uses it tests aluminum 7075 T6, and the offset method was used here to indicate the yield stress of both of these specimens. And basically, it shows that the aluminum Al7075T6 showed a higher yield stress than aluminum 7075 T651 in these tests.
The next we have the dynamic tension for this aluminum alloy. There was used with the hole length, diameter, and the gauge length of specimen is 34, 4, and 12 respectively. And the both ends of the specimen manufactured in a screw shape in order to be fixed in incident and transmitted bars. And this specimen was tested in a room temperature. As we can see here, there are like two graphs for a different strain rate. This one is for 2000 per second, and this one is for 1500 per second. We can see there is like some changes, actually important changes. And we can go with next slide, I guess. Here are the mechanical properties. Here we can see that it's important that for 7075 alloy, that its mechanical properties, its tensile and yield strength changes according to its aging state, according to its tempering. There is a trend of when you age it, the corrosion resistance increases, but the tensile strength decreases. But when you overage it, the tensile and yield strength increases, but it worsens its corrosion resistance. Yeah, please, Ahmed, go on with the next slide.
Now I'll be explaining and discussing the mechanical properties of aluminum 7075. And aluminum 775 and its temperates are widely used in different industries, as stated before by Gülşah, due to its high strength density ratio, high ductility, and the high fatigue resistance. And in table 3, you can see the several mechanical properties of aluminum 7075. It has a Young modulus of 16 gigapascal, a yield stress of 105 yield stress in megapascal, and as stated before, different temperates of aluminum 7075 are widely used, but here in table 4 and table 5 we maintain the two of them. And I think it should be highlighted that the elongation percentage of aluminum 7075 T6, it's 11%, and I think like it's one of the indicator that our material is quite ductile, even after the trade-off to increase the yield tensile strength. And also I want to include that the average elongation percentage of the ductile material is just 5%, so ours is just 11%. And finally, we can talk about fracture type of aluminum 7075. Here in these images, we can see that the fracture type of the specimen, and at the bottom we can see the specimen. And these are the conditions: 300 Celsius and the 3100 strain rate. And here you can see that the fracture takes place gradually, which is one of the features of ductile material. Also, we can see that the fracture is not perpendicular to load applied or force applied, which is another indicator that our material is ductile. And in conclusion, fracture type, a high elongation percentage, stress strain diagrams, and the other mechanical properties such as high plastic deformation ratio takes us to the point that our material, aluminum 7075, is quite ductile material. And here we have 10 references, all academic papers. Thank you for listening.